All right, so let's get started on chapter 9, where we will talk about gases and substances that take on that physical state, the gas phase. In chapter 10, we will look at the other two phases of matter, liquids and solids, but for now, we'll look at gases. And so in this chapter, there are no blanks within the actual definitions. The only blanks you'll see are in worked out word problems, but obviously, I will add supplementary notes to those lecture slides with definitions. Chapter 9 is a little bit more math intensive than we've dealt with in the last two chapters. We'll be looking at the ideal gas law that you might be familiar with and other types of calculations. All right, so let's get started. All right, so when investigating gases, we can look at a gas two different ways. We can ignore intermolecular forces and the volume of the actual gas particles, and in this way, we are considering gases to be ideal. And so that's the first, I guess, four sections of this chapter that we will consider gases to be ideal. And this is a great way to relate volume, pressure, and temperature of gaseous samples is to look at them from an idealized lens. But, gases that exist in the real world don't always behave in this ideal manner. And so we do have to consider intermolecular forces and the actual volume of the particles. And this is what brings us to non ideal behavior, or we can consider gases to be real gases. And so that's the last part of the chapter. So first, let's look at gases in an idealized manner. So we've seen gases in our balanced chemical equations. You know that we always indicate the state of matter after each chemical formula. So some of the gases that we've already, experienced and can recognize are these low molecular weight diatomic elements and some others. So some other gases that you've seen in chemical formulas: hydrogen gas, nitrogen gas, CH4 is methane gas, CO2, carbon dioxide, that's in our air, what we exhale, and O2 gas, that's what we breathe in. These are common gases that we have experienced already. And so a common theme here that you see is that all of these gases consist of non-metals only, and they all have low molecular weights. And that lends themselves to have gaseous states at standard temperature and pressure, or at room temperature on Earth at 1 atmosphere of pressure. So all of these gases have common properties and reasons that they are gases. They all have relatively low densities. We measure density of gases in the unit of grams per liter, versus, for solids and liquids. We've already kind of looked at this already. Density of solids and liquids are oftentimes measured in grams per centimeter cubed, or grams per liter, or sorry, milliliter. But for gases, because they have low densities, we have to change the unit a little bit, grams per liter. So we're looking at a larger volume of sample and weighing that, versus solids and liquids are much more dense. So we look at a smaller volume of sample to get that mass. So yeah, gases have low densities, so they are measured in this unit instead. Gases are also compressible. So they can change their volume. So I'll say can change volume easily. Versus liquids and solids, you can squeeze on a solid sample and not change its volume. But for gases, you can change its volume. So this will bring us to some of the gas laws, where if you change the volume of a gaseous sample, something else needs to change. Gases also expand to fill any container. We experience this when we blow up a balloon, when we exhale our breath, mostly CO2 and water vapor, and fill up a balloon. Our breath is filling up that whole balloon, the whole volume of that balloon. And then also gases exert pressure on the outsides of walls of their container. And so these are things that we'll be able to measure, properties of gases. These are things that we can measure in lab, things like pressure and volume of the container that gas occupies. So what you'll see when we get into the gas law calculations is that there are different properties of a sample of gas that are all related to one another. When you change one type of property or measurement that you make in lab, if you change that in a gaseous sample, then something else, some other property also must change. And that's what brings us to the gas laws. So these are different things that we can measure in lab of a gaseous sample. So things like pressure, volume, temperature, and quantity. We'll see that all of these properties are related to one another in a gaseous sample. So what's important here, and we'll get to this later, all of these quantities are related to one another depending on the type of constant that we introduce, and this is related to the gas law constant that we use, R. R is a constant, and the unit of R that we use has a specific unit. That unit is liter, ATM, mole, Kelvin. So it's important when we measure these different properties of a gas that we always maintain or use the units that are within our R constant. So when we measure pressure and put it into our gas law equations, pressure needs to be measured in ATM. So keep this in mind when doing these calculations. Volume also must be measured in liters of a gaseous sample. Temperature needs to be measured in Kelvin, and quantity of our sample needs to be measured in moles. So we can't just put any old unit into our gas law equations. We need to make sure that we use the specific units that relate all of these different properties to our gas law constant. All right, so let's go into a little bit more detail of all of these different physical measurements, physical behaviors of gases. So that first one is pressure. So pressure of gases is a very important quantity to understand. Pressure of a gas in different aspects of our life, different applications, that pressure, that measurement is very important because it's different in different spaces. So the pressure of the air that we breathe is different than the pressure out in outer space. It's one of the reasons that we can't breathe in outer space. The pressure is very low out there. The pressure of gases in our car engines is slightly different depending on what type of octane rating that your vehicle requires. So anyway, pressure is defined as a force per area unit. Where that force is coming from, it's coming from the gas. So if we remember one of the properties of gases, gases exert pressure on the walls of their container. So there's a force being pushed onto the walls of the container from the gas particles themselves. So that lends itself to the definition of pressure. Pressure is equal to force per area. All right, and so the atmospheric pressure, that we experience every day, that is also a force per area. So essentially, where that force is coming from, that force is coming from all of the gas particles above our head in the atmosphere. Our atmosphere is made up of gas particles. Diatomic nitrogen, oxygen, methane, a little bit of methane, a little bit of CO2, a little bit of water vapor. All of those gas particles, if you think of it as like a column above your head, all the way out into outer space. If we count up all of that mass of gas and apply gravitational force down and count all of that up, you will see that the pressure of our atmosphere is about 14.7 pounds of gas particles pushing down on a square inch of our heads. So that is atmospheric pressure. Typically, especially in our gas law calculations, we'll usually use the pressure ATM. So it's defined on Earth. At sea level, we have 1.00 ATM, or atmospheres of pressure, at sea level. And so this is also equal to that 14.69 pounds per square inch, or PSI, unit. So both of these values are pressure units. So you might be familiar with the unit PSI because that's the unit of pressure we typically insert into our car tires. So my car takes like 32 PSI of pressure in its tires. That's what the manufacturer dictates. So that 32 pounds per square inch that the manufacturer says to put into the car tires, that is pressure above atmospheric pressure. So that's the increased pressure inside those car tires. So when I fill up my car tires, I just use the machine that's at the gas station. But in the scientific realm and the chemistry realm, there's other ways to measure pressure of gases. So within the weather community, we can use a barometer to measure atmospheric pressure. You saw the barometer in our chemistry lab on the front wall, and so that instrument measures the atmospheric pressure in that room. So you'll see that it's not quite one atmosphere at all times. If you watch the Weather Channel, you might hear the weather person say we're in a low pressure system or we're in a high pressure system, and that just means that the air pressure in that area is either slightly higher than 1 atmosphere or slightly lower than 1 atmosphere. So a high pressure system, if we're in that, will be if the air pressure is slightly higher than 1 atmosphere. But typically, at least how we dictate air pressure at sea level is 1 atmosphere. But we also use the unit millimeters of mercury, and that is equal to 760 millimeters of mercury. Why mercury? That's because old-time barometers used mercury, which is a liquid metal, to measure air pressure, because mercury is very dense, and the weight of it can counteract the atmospheric pressure that is on the outside. So this is essentially the diagram for a barometer. So you can see here there's this inner tube that's open to a pool of mercury, and so inside the barometer there's a vacuum. So there's no pressure being exerted from the airspace here. So all the pressure is coming from the weight of mercury itself. So when atmospheric, you put this instrument in the atmosphere, or just like on the bench top, the atmosphere is going to push down on the pool of mercury and then push up on the tube or the inner column of mercury here. So the weight of this inner tube of mercury is equal to that of the pressure, the atmospheric pressure being exerted on the outside. So again, here, the question is, why do we use mercury within a barometer? Why don't we just use water or something? Well, if we did use water, this column would have to be very, very tall in order to get enough mass of water and weight of water to equal that of atmospheric pressure. I think here it says if we used water within this column, it would be over 34 feet high. So we use mercury because it's very heavy and it can counteract the pressure coming from the atmosphere. And so with this apparatus, what you'll see, if you set this up, at exactly 1.00 atmospheres, this column of mercury, the weight of that mercury to equalize the outside pressure will be 760 millimeters of mercury. And so that is a unit of pressure that we also use. So if we think about our toolbox of units of pressure that we've already looked at, there's atmospheres, there's millimeters of mercury, and there's PSI, or pounds per square inch. One other unit that we often use is also called torr, which is the exact same unit as mercury. So 760 millimeters of mercury can also be written as 760 torr. So torr and millimeters of mercury is exactly the same thing. So I have that here. All the units of pressure that we've already talked about in this slide are different measurements. 1 atm, which is just our earthly atmosphere, is 760 millimeters of mercury, or 760 torr. So they're the same thing. So I'll just say 1 millimeter of mercury is also equal to 1 torr. And then we've also talked about PSI, or pounds per square inch. So 1 atmosphere is 14.69, 14.7 psi. Another unit that physicists often use, but it's less commonly used, but using our SI units that we've already talked about, is the Pascal. A Pascal is 1 Newton, which is a unit of force that you might have experienced in a physics class, over a meter squared. So meter squared is our area. So a meter is a length, and so if you square it, there's our area. And so how atm, millimeters of mercury, and Pascal are all related to one another. 1 atm is 1.012325 times 10 to the 5 pascals. So this number is a little bit ugly, and so chemists don't typically use them. We typically measure our gases in units of either atm, millimeters of mercury, or torr. But in a physics class, you might use Pascal, and I think on maritime, or like on boats, they use the unit of kilopascal. So if you're into boating, you might see that unit of kilopascal. So we have all of these different units of pressure. So you can see how questions can easily arise from here by converting different units of pressure to one another. So that's what we're going to do here. Convert some units of pressure to other units. So here's a problem. The pressure inside a incandescent 25 watt light bulb, people don't really use incandescent lights anymore, is 4.60 millimeters of mercury. what is that pressure expressed in atmospheres? So we want to go from the unit of millimeters of mercury to ATM. That's what this question is asking. So the conversion that we need to use comes from all of these definitions that we just came up with, or that we've introduced, that 1 ATM is equal to 760 millimeters of mercury. There's the equality that we need to relate millimeters of mercury and ATM. So I'll just rewrite that definition here so I have it. 1 ATM equals 760 millimeters of mercury. So there is the conversion, or sorry, the equality that I need, and I can turn that into a conversion factor to convert to the unit that I want. So again, typically how you approach problems like this, or word problems, is you take the number and the unit that the problem gives you. So start with 4.60 millimeters of mercury. Our goal is to get to ATM. So let's turn this equality into a conversion factor that gets us the unit that we want. So right now I have the unit millimeters of mercury. So I want to put this part of the equality in the denominator. So 760 goes on the bottom, and then 1 ATM will go on the top. Perfect. And so you stick that into your calculator. I'll let you know that these are exact numbers. So our sig figs at the end will have 3 sig figs, and so I don't have, oops, I should have done this already. So 4.60 divided by 760 equals 0.00605 ATM. All right, and that's with 3 sig figs. To convert this into scientific notation, because there's a lot of zeros there, so I can move that decimal place 1, 2, 3 times, and since it's a small number, it will have a -3 exponent, or because I moved the decimal place to the right. But I just remember, okay, this is a small number, so the exponent should be very small, or the exponent should be a negative number in scientific notation. So this answer would be, yeah, it's written right here. So 6.05 times 10 to the -3 ATM. All right, so the next question here, tire pressure gauges are marked in PSI, or pounds per square inch. So here I am nice and just give you the conversion factor, or the equality you need to convert between PSI and ATM. But in this question, it says your car tire gives a reading of 33.4 PSI. Express this number in units of millimeters of mercury. All right, so the conversion factor that I give you doesn't relate PSI to ATM directly, but thankfully we used an equality that relates ATM and millimeters of mercury. So we can just use that conversion factor as well, in addition to this other one that they gave us. So I'll just rewrite that here. 1 ATM equals 760 millimeters of mercury. And so if we write out a kind of like a timeline or a strategy or roadmap of the units that we have to go from, let's start with the value that's given. So that's in the unit of PSI. From PSI, we can use the conversion that's given, PSI to ATM, and then ATM to millimeters of mercury, and that's what the question is asking for. So let's set this conversion, or this dimensional analysis up. So start with the value that's given, 3.4 PSI, times, so this first conversion factor, or equality, is 1 ATM equals 14.7 PSI. I want to put the PSI part of the equality on the denominator, so 14.69 PSI, 1 ATM on top. So now if you inspect the units, PSI cancels. If we stopped right here, we would just get the unit of ATM. So we don't want to stop here. Our goal is to get to the unit of millimeters of mercury. So we'll have to do one more step, but thankfully we have that conversion here. 1 ATM is 760 millimeters of mercury, so I'm going to put 1 ATM on the bottom, 760 up top, and then you can see how all of the units cancel, ATM, ATM, and now we're just left with millimeters of mercury. So if you stick that into your calculator, you get 1,730 with 3 sig figs millimeters of mercury. And that's because our value that's given is, has 3 sig figs. 3 sig figs. All right, and so there's our answer. All right, so now that we have a grasp on pressure, let's look at some of the named gas laws that relate pressure and some of the other properties of gases that we've already talked about. So Boyle's law is the first named gas law we'll talk about. The reason we call these the named gas laws is because all of these laws are named after a different scientist who discovered these relationships. So with these named gas laws, it's important to note that typically one of the properties, temperature, volume, or pressure, stays constant, and then the other two variables or the other two properties are related to one another. But it's important to note that one of the variables has to stay constant. And these changes that we're doing are changes to one sample. So I'll kind of explain that in a little bit. But so Boyle's law states that at a constant temperature, so temperature staying constant, volume of a gas varies inversely with the pressure exerted on it. So these two graphs kind of demonstrate volume being inversely proportional to pressure. And then this relationship also dictates that volume is proportional to 1 over pressure, that they're inversely related to one another. Or you can think, as volume goes down, then pressure will go up. They're inversely, if one goes up, the other goes down. So that's what it means when they're inversely proportional. Or if volume goes up, then pressure goes down. They're inversely proportional. And again, this has to be at a constant temperature of one sample. So we're making these changes. If we change the volume, we're changing the volume of a sample. And we're looking at the same sample after we change that volume. So, this relationship of being volume and pressure being inversely proportional is kind of makes sense intuitively if we think of like a balloon that I blew up with air from my mouth. That balloon contains a sample of gas, and that balloon has a certain volume and a certain pressure. So if I squeeze on the balloon, what I do is I decrease the volume, but the amount of gas in the balloon still remains the same because all of that gas I gave from my lungs. And so when we squeeze the balloon and we reduce the volume, the pressure inside the volume increases. Because if I let go of the balloon, then the balloon will spring back to its original volume. Or you can think of a piston that has a certain amount of gas in it. If I squeeze the piston and reduce the volume, the pressure goes up. Or if I expand the piston, so we're essentially giving those gas particles, the same amount of gas particles, more room to expand and to move around, then we decrease the pressure. So if you increase volume, you decrease your pressure. And so that's what Boyle's law states, that volume and pressure are inversely proportional, but this is at a constant temperature looking at a specific sample of gas. So I'll write that there. Looking at specific, I'm spelling this wrong, specific sample of gas, meaning that the sample of gas is not changing, that the amount stays the same. So amount stays the same. All right, so that's pressure and volume. All right, so let's look at the next gas law, Charles' law, named after Jacques Charles. So he says at a fixed pressure, volume of a gas is proportional to the temperature in Kelvin. So that's an important note here. But see how I've stated this gas law is very similar to the previous one, where we dictate what is staying constant. So in this case, pressure is staying constant. Volume, if you fix your pressure, then volume and temperature will increase together. They're proportional to one another. So in this case, we write out the relationship that volume is proportional to temperature. So if volume, I'm going to say if temperature goes up, then volume also must go up, and then the opposite. If temperature goes down, then volume goes down. And so you see that relationship here in this graph, that you see that they're increasing together. But the important thing to note here is when we're making this relationship and doing calculations, temperature must have the unit of Kelvin. That is the only way for calculations to work. I mean, we can kind of just conceptually say volume and temperature increase together, but in calculations, temperature must be in the unit of Kelvin in calculations in order for everything to work out. So let's just keep that in mind. Temperature must be in Kelvin. And with all gas equations that we're going to use in this chapter, temperature always must be in Kelvin. So I'll just write that equation here. So our temperature in Kelvin is equal to our Celsius temperature plus 273.15 Kelvin. So all gas equations must use our temperature in Kelvin. So keep that in mind. All right, so again, we probably have some intuition here and understand that if you increase temperature, volume goes up. If you think about a hot air balloon or something, so here's a picture of Jacques Charles and a hot air balloon. So how hot air balloons work is that, the balloon, when it's deflated, when your hot air balloon is deflated, it's just like a big bag on the ground. But then you have a source of heat, and a little bit of fire, and you pull on the lever and you heat up the gas or the air that is in the balloon itself. And so when you heat up the gas, you're increasing the temperature of your sample. And so what you see as you pull on the lever to supply heat to the gas is you see that the hot air balloon expands and starts to fill up the whole container or the whole hot air balloon itself. So there's an example where if you increase the temperature of the gas in the hot air balloon, the volume of the hot air balloon expands. And then as it expands, what the reason that hot air balloons work is that when that volume of gas expands, it becomes less dense than the density of the cold air around it, thus giving you enough lift for the hot air balloon to go into the air. But a hot air balloon demonstrates how temperature and volume are directly proportional to one another. If temperature goes up in the inside of the hot air balloon, then the volume of the hot air balloon increases. Conversely, if you shut off the heat and then the temperature of the gas starts to decrease, then you'll see your hot air balloon start to shrink. And so as a little side note here, we've talked about the temperature scale of Kelvin before and how many calculations require the use of the unit Kelvin instead of Celsius and definitely not Fahrenheit. So where we actually get the unit, how scientists calculated the Kelvin unit, essentially how did they come up with that we need to add 273.15 to get to a Kelvin temperature from Celsius? Like, where did this come from? It actually came from gas law graphs like you see here. So it was actually Charles' law in which you can derive the Kelvin temperature. So essentially, you can derive Kelvin temperature from Charles' law type graphs where we graph volume versus temperature. If you extrapolate back from the point of volume to reach zero, like a zero volume, what temperature would that occur at? That gives us our negative 273 Celsius. So in order to have a zero volume of a gas sample, which is not theoretically possible because the gas particles have a volume themselves, but these are ideal gases, if you extrapolate the graph backwards, you would get that the temperature at which a gas sample would have a zero volume would be negative 273 Celsius. And then that is what we call 0 Kelvin, is the point at which volume equals 0 for a gas sample. So the last gas law that we will talk about relates the two variables that we have not related yet, and that's pressure and temperature. So this is Gay-Lussac's law that relates pressure and temperature. And so you can see from the graph that they are directly proportional to one another. So pressure is directly proportional to temperature. So if temperature goes up, then pressure also must go up. And then the same. If temperature goes down, pressure goes down. And so with this relationship, you have experienced this on cold winter days. So like the first cold winter day or cold fall day of the year, you might see on your dashboard your car tire lights go on, meaning that you have low pressure inside your tires. So how Gay-Lussac's law is being demonstrated here is that in the first cold day, temperature is down. So it goes down. So what's happening is that the pressure inside your tires are also going down. And then if the pressure goes down low enough, then the sensor inside your car tells you, hey, you need to put air into your tires. So that reasoning uses Gay-Lussac's law, where temperature and pressure are directly proportional to one another. And with all of these gas laws, it seems like hot air balloons are being used a lot, just because hot air balloons really demonstrate the use of temperature control, volume changes, and pressure changes, with all confined within a hot air balloon. So here is a picture of Gay-Lussac. In a hot air balloon, how many meters, or 2,300 feet in the air, in a hot air balloon to collect samples at different height measurements. So he's a very daredevil scientist to, get those samples that he really needed. All right. So those are the three named gas laws that you need to know. But thankfully, we don't need to memorize all of these laws individually. We can actually use one equation to explain all three of them. So we can combine all of the gas laws into what's called the combine all of the named gas laws into one law, called the combined gas law. So what you see here is that both Boyle and Charles' law use use volume in their relationships. So we know that volume and pressure are inversely related to one another. Volume and temperature are directly related to one another. So we can combine those two laws together and say, okay, volume is proportional to temperature over pressure. So to turn this relationship into an equation, if we turn that proportional sign into an equal sign, and if we multiply both sides by pressure, so it cancels out there, and then we divide both sides by temperature, or 1 over temperature. So then this temperature cancels. What we are left with is pressure times volume over temperature equals some constant. And that's what you see here. So for any given sample, so the same gas sample under different conditions needs to follow the combined gas law, where pressure of one state, so we're changing the sample in some way. So the pressure, volume, temperature of one state is equal to the pressure, volume, temperature of its second state or second condition. So how you derive one of the named gas laws is if one of the properties is held constant, then you can just leave that out of the equation. I mean, you can include that in the equation, but you don't have to. So for example, if pressure in both your first condition and your second condition that you're changing to is 1 atm, right? So pressure is just 1 atm. You see that since it exists on both sides of the equation, you can just cancel those two values out. So that's how you derive one of the named equations from the combined gas law. If it's held constant, then just cancel that property out of the equation. So let's do some problems here that use the named gas laws, but really we'll just use the combined gas laws numerically to look at these questions. So let me just write that down here. So P1 V1 over T1 equals P2 V2 over T2. So my strategy for gas law equations is first identify what is changing. So I'll write that down. My strategy is what property, so that means pressure, temperature, volume, whatever, is changing, and then what stays constant. In some cases, nothing stays constant, and that's okay. As long as only one of these variables is unknown, then we can still solve for it. What stays constant? And then at that point, it's just plug and chug. So let's look at this problem. So we have at a constant temperature, that's a hint, of 1.60 atm, a sample of CH4, that's our sample, occupies 8.32 liters at 350 Kelvin. At what volume will this same sample occupy at 420 Kelvin? All right, so let's break this down. So pressure here is staying constant. So when using the combined gas law, we don't have to include pressure, but we can. So I'll just write here P1 equals P2. That's what it means when it says the pressure is remaining constant. P1 equals P2, and it equals 1.60 atm. So we don't have to include that in the equation. But if you do, you'll still get the same answer. You just have to make sure you have 1.60 on both sides of the equation. So we have a sample. It occupies 8.32 liters at 350 Kelvin. So liter, that's a volume. So I'm just going to say that is V1. That 8.32 liters is V1. That's a volume. 350 Kelvin, that's its temperature at that same point at that volume. So that makes that T1. All right, so let's look at what we have so far. So we have V1 and T1. That's great. And so now this question is saying, what volume will this same sample occupy at 420 degrees Kelvin? So we're changing the temperature. So this is T2 because we've changed the temperature. And so we have T2. And now you can see it's saying, what is the volume at that T2 temperature? So we are solving for V2. Right? So let's just rewrite this equation without the pressure number in it. So it's V1 over T1 equals V2 over T2. So which gas law is this? Which gas law relates volume and temperature? Well, it's Charles' law. But we didn't really need to know that just because if we just use the equation in the combined gas law, the numbers will work itself out. So let's, what are we solving for? We're solving for V2. So let's just move values around to isolate V2. So V2 equals V1 T, whoops, that should be a 2, sorry. V1 T2 over T1. So since T2 is in the denominator, I'm going to multiply it, T2 on both sides, all right? So now we just have to plug in our numbers that we've already identified. So V1 is, I said that, 8.32 liters over, times T2, which is 420 Kelvin, over T1. So 350 Kelvin. So the important thing here is to definitely keep track of your V1, T1, your ones and twos. What are the properties in your condition 1 versus your condition 2? So make sure those numbers, match one another. And so if you stick that into your calculator, you get that the pressure is, oh, I didn't do this. Here's my calculator. So 8.32 times 420 divided by 350 is 9.98 liters. All right, so let's just think intuitively, does this make sense? So we want to know what is the new volume if we increase our temperature. So we're using Charles' law. Charles' law is like our hot air balloon. So if we increase our temperature, our volume should go up. So let's see if this answer actually makes sense. So we're increasing our temperature from 350 Kelvin to 420 Kelvin. So we would imagine that our T2, our V2, our new volume will be larger. And in fact, it is, that our volume goes up to about 10 liters up from 8. So this answer makes sense. And again, if you wanted to include P1 and P2, where it's 1.6 in both cases, you will get the same exact answer. But in this case, because it stays constant, we can leave it out. And the last thing to note here is that all of the units that we need to cancel do in fact cancel out. So you see how Kelvin in T1 and T2, those two cancel, leaving us with the unit of liters here. So the important thing with units when using the combined gas law is that one, temperature, T1 and T2 must be in Kelvin. That's the big thing. But volume and pressure, it doesn't matter what unit you use as long as it's the same unit in condition 1 and 2. So whatever your volume unit is in V1, you will get the same unit or should use the same unit in V2. Same thing with pressure. I could do this question in PSI. It doesn't matter as long as P1 and P2 are both in that same unit. And that's only for the combined gas law. So we just need to make sure it matches on each side. All right, so let's do another question here. So we have a sample of gas occupies 2.0 liters at 8.60 atm at 0 degrees Celsius. At what temperature will the gas display a pressure of 10 atm if it is pumped to a 5.00 liter tank? So let me just rewrite our combined gas law. P1, V1, T1 equals P2, V2 over T2. So let's go through this question and identify P1, V1, and T1. So our condition 1 and our condition 2. So I'll just read through the question again. So a sample of gas occupies 2.0 liters. So that's a volume. So I'm just going to say that that's V1. At a pressure of that, so 8.6 atm, that's a pressure. So that's P1. And at 0 degrees Celsius. So this is T1 as well, but it needs to be in Kelvin. So 0 degrees Celsius to Kelvin is 273.15 Kelvin. But it would be rounded to the ones place, so we can just say it's 273 Kelvin. All right, so we have defined P1, V1, and T1. So I'm just going to put little check marks there because I know all three of those. Next, it says, okay, at what temperature? So we're solving for a temperature. And I mean, we already know T1, so that means that this temperature must be T2. It's, what is the new temperature that the gas display will display at a pressure of 10 atm. So this is a new pressure. So this is P2 if it is pumped into a 5-liter tank. So this would be V2. So it seems like V1, our volume, is going from 2.00 liters to 5.00 liters. So this is like our condition 1, or our first state of this gas, and our second state of our gas. We're changing the volume, we're increasing the volume. What's happening to the pressure? It is going from 8.60 atm to 10 atm. So we're increasing the pressure. And then finally, temperature. It's going from 0 degrees Celsius or 273 Kelvin to some new temperature. So we don't know this. This is what we have to solve for. So we can't use just one of the named gas laws directly because too many things are changing. Nothing is staying constant. So this question requires you to use the combined gas law. That's okay because we know all of the values that we need to insert into this equation. There are 5 different values here. So if we insert 5 of them, because we know P2 and V2, all we have to do is solve for the last one we don't know. And so in this case, it's T2. All right, and so if we rearrange the combined gas law equation, so P1 V1 over T1 equals P2 V2 over T2. All right, so we want to isolate T2 here. So if I multiply both sides by T2, that will cancel T2 out, putting it in the numerator side on the other side. All right, and then I also want to multiply both sides by T1, because in that case it puts T1 on the other side of the equation because we want to isolate T2, and then we want to divide both sides by P1 V1. So we isolate T2. And so, excuse me, the new equation will be T2 equals, so let's cancel some stuff out so it's easier to see. So P1 V1 cancels there, T1 cancels there. All right, and so we're left with, let's do a different color. T2 equals P2 V2 T1 over P1 V1. So that's what it is. So T2 equals P2 V2 T1 over P1 V1. So you can see that this equation works out because we have pressure volume on the top and it should cancel with pressure volume on the bottom, leaving us with whatever unit T1 is will be T2. And so if we stick in all the values there, so T2 equals 8.60. Oh, wait. No. So P2V2, that's right here. So P2V2, so 10.00 liters. V2 is 5.00 liters times T1 is 273 Kelvin over P1 that's 8.60 liters, or sorry, ATM. And then volume is 2.00 liters. And then you just stick that in your calculator and you see that, 10.00 ATM, I'm sorry. You see that ATMs cancel, liters cancel, leaving us with the unit of Kelvin. And so if you stick that into your calculator, you should get that Kelvin. Our new Kelvin temperature is 794 Kelvin, or about 521 degrees Celsius. So again, remember, because T1 is in Kelvin, that's the temperature T2 is in. But in order for the combined gas law to work, temperatures must be in Kelvin. If you do it in Celsius, it's not going to work out. All right, so what this question really exemplifies and tests you on is your ability to read the question, inspect the question, and be able to identify what is changing, identify what is P1, V1, and T1, P2, V2, and T2, and solve for what the question is asking. And so the combined gas law uses up all of the topics of the named gas laws that we just went over. But in this case, for this question, because everything is changing, we can't predict, because volume is going up, pressure is going up, We can't really predict with certainty, which direction temperature is going to go, especially if some of the named gas laws are going in different directions with one another. But as long as you use the combined gas law, then you'll always be right.